Good afternoon. This is CIVE632, and today is the second class of the sixth week, Wednesday, September 29, 2021. And the subject today is diffusion waves, more on diffusion waves. So I'm going to share the screen here for you, and we can get started. Let me see if I'm doing this right. This lecture today is going to be interesting because for two reasons. First of all, it is some of the work we have done, some of the best work we have done actually in this area. We, meaning myself, with my students. I've had a number of students, very good students over the years. And also, it is a difficult subject. So hold your horses there and sit, hold on to your chair, as they say, because I'm going to go over the equations, but I'm not going to dwell on it. I figure I don't have to teach you algebra. This stuff is algebra, but it's some of the most complex algebra that you will ever see, okay? And that is the reason why Vedernikov was confused, and then Chow didn't look at it. Powell was confused, and many others, starting in the year 1946, 45, I think. That is when Vedernikov came up with this relation on the roll waves, on the stability versus instability. And we had to wait until 1991 and for me to work several years on this and develop what happened. And it was all mostly luck. I mean, I was at the right place at the right time. Okay, so we call this new perspective on the Vedernikov number. The Vedernikov number had been studied by a bunch of people, namely all the ones that I already told you. Kriya did great work. Doug also did great work, but they quite didn't zero on the Vedernikov. I'm sorry, Doug did not zero on the Vedernikov, but Kriya did. And then subsequently, Kibler, who was a student of Woolheiser, he was a professor and became chair of civil engineering somewhere out there on the East Coast. And Kibler also wrote about the Vedernikov number extensively. So the work that I am reporting here was based on all the writings that had been done until the late 1980s. And then in 1990, I wrote this paper because I was ready to do it. I basically discovered that Doug had done very good work, but he did not finish it. So I finished the work of Doug, basically. Doug and his associates, okay? So the short story is that for some reason, Vedernikov made it very confusing because it could be confusing. And the other people did not bother to interpret it. Now, I happen to know, I was knowledgeable with the S-curve, and the S-curve helped me a lot to understand what was going on. The issue with Vedernikov is very simple, extremely simple. It's so simple that it's almost ridiculously simple, okay? How many characteristic velocities are there in open channels? There's three. There's the mean flow velocity. Two, well, there's one, the mean flow velocity. Second, the relative celerity of kinematic waves. Note that I put relative celerity, the celerity relative to the flow, that I call V, and the relative celerity of dynamic waves, W. Note that kinematic waves are the Lychet-Whittam kinematic waves, and the dynamic waves are the waves of Lagrange, because the waves of Ferret don't have a celerity. That's the thing about the dynamic wave of Ferret doesn't have a celerity because it's in the middle and it changes with the wave number, okay? So these three speeds give rise to only two independent dimensionless ratios. And these are V over U, which is the dimensionless relative celerity of kinematic waves. So we take the celerity of kinematic waves and divide it by the velocity of the flow. In the dimensional relative celerity of dynamic waves, we take W and U, and that becomes those two. The third ratio is the Vedernikov number. The Vedernikov number pops up as the ratio of the first two that I already mentioned. I also say in here that the Freud number is the reciprocal of the first one or the second one. So basically, I mean, if you want to do some Monday morning quarterbacking here. I think Freud must have made a mistake. He should have defined his number as a reciprocal, because that's the one that really makes a lot of sense from this presentation. However, I already told you, Freud did not mention his number. He was just ascribed the number later on. So, and they were going to do what they were going to do. And they didn't know, they had no way of knowing in the 1900 that all this stuff was going to come up in 1991. Okay, recent developments in the linear theory, that is Dug, right, show that the Vedernikov number has a significant role in extending the concept of hydraulic diffusivity to the realm of dynamic waves. That's what Dug did. This new perspective makes possible the modeling of catchment dynamics using diffusion waves and including inertial effects. So in here, we're going to extend the Hayami theory to the purview, or to have the capability to include inertial effects under a wide range of boundary friction and cross-sectional shape specification. That's what we're going to do here today. Clarify the issue of how does the boundary friction and the shape specification come out. Now, the boundary friction is a simple matter. It's either laminar, turbulent, or transitional. But the cross-sectional shape is not. It's not. And so this is where the stuff is going to be a little bit difficult from now on in this paper. So there's three characteristic speeds, and I repeat this stuff already. Recent developments, and I mentioned Dug, 1973, that's the paper we read. And then Dug et al., 1982, that's the paper we are going to read today. Well, not read it, but we're going to talk about it. Dug et al. The et al. Are two Polish gentlemen that went from Poland, presumably, to Ireland, because Dug was in Ireland, to study the stuff, to study under him. Dug at the time was a very well-known professor. And they contributed this paper. I'm given to understand that they were with Dug on this. Dug came as the major author, but they must have done the work. And it was, I'm going to describe it here, it was crazy work. It was so crazy that, crazy difficult, that I had one of our students, Nucitelli, I forget her first name. Nucitelli was a math whiz. I've had a lot of math whizzes as students. The first thing I asked them, if you know math, oh yeah, we do it. I charged Nucitelli with a special study to unravel the Polish gentleman, the paper written by the Polish gentleman. Unravel means you disaggregate it. You explain to us what they did, okay? Because they got an answer. And the answer of the Polish people was what I wanted. But they have 5 pages of math in there that I don't think anybody's save Nucitelli could do it with 3 months of work. And she actually didn't come up and do it completely. She did 90% of it, which was good enough for me. We're not, getting a lot of credit for this. So we just said it is what it is. Okay. So that's the story on how that got done in the year 2014, I believe this is when. Let me see this paper in here. No, this is 1991. This is even much earlier. So some of the stuff, some of the stuff you have already seen me talking about it. Other is relatively new. Okay. So the Vedernikov number is defined as, and this is the definition by Chow based on Vedernikov. So Vedernikov had a friction value and a cross-sectional value in there. Vedernikov equal Freud times friction and cross-section. This, of course, gives us the impression, I'm going to try to go fast in here. This gives, otherwise we won't finish. This formula gives us the impression that the Vedernikov number is a surrogate, or rather an appendage of the Freud number, and that is not correct. They're totally independent. They're totally independent. They sit on their own base. But the way Vedernikov wrote it and the way Freud wrote it is like they were focused on the Freud number and they wanted to make the Vedernikov a function of the Freud number, and that is not correct. But that's where they actually messed up, I think. Where's X? X is an exponent of hydraulic radius in the Reynolds number of the Darcy-Weisbach. So X is responsible for friction, okay? The parameter B ranges, we've said there's a parameter that was put in there. This is all Vedernikov's work, by the way. Gamma is an invention, very smart invention of Vedernikov. gamma is going to be 1 minus RdPdA. When I first looked at this, and I'm going like, how are we going to work with this? And then I charged Porras, who came over in 1995, just to work with me. He said, Porras said, Professor Ponce, I want to get a master's under you with a thesis. I said, great. So I gave him the book by Liggett, 1975, and I said, study this. The subject was stability. This is what we're going to do, stability. It's a new subject. Yeah. And Liggett had scratched on the surface. Like a very good researcher, he scratched on the surface. He says, this is what needs to be done. These are the equations, the basic equations. Great job. Great guy, Liggett, by the way. I don't really know where he is right now. Well, he retired, I'm sure, many years ago from Cornell, teaching at Cornell. Okay, so the shape factor, then I charged Porras that he should unravel this equation, this equation number 3. Explain to us what exactly does it mean. And he did. It took him a while, but he did. With my help also, we finally found out that this equation 3 is based on this equation here that we don't put a number. A power function of P with A, case of 1 and D, these are exponents, coefficient and exponents. So we have the derivative with respect to A, and then we can plug in the derivative, and then we'll recast the Vedernikov number at x1 minus D. It's a somewhat simpler way, now explainable way, of how the Vedernikov number was written. Because this other equation is confusing. It's confusing to me, I don't know if to you, but you have to look at it carefully. The inherently stable channel is a hypothetical channel in which the hydraulic radius is a constant. So here came the issue of Liggett. That Liggett said we could design a channel that looks this way, where the hydraulic radius is a constant, and it will be stable, completely stable. He did not call it inherently, because I invented that word. I said it's inherently stable. You can't mess with it other than it to be stable, completely stable. No rollways in this channel, because this cross-section is controlling it, as Vedernikov had said earlier. Okay, so that's the inherently stable channel. We already talked about that. I give credit here to Kriya, who clarified it. And I remember I told you already what Kriya did. He apparently was working at the same time, but he was working in France, not in Russia. So he decided to come to the United States in 1952. It took him a few years. In 1952, published a paper on this subject, which is a very good paper. It has a few errors, but it's a very good paper. Also very difficult to read. Okay, so essentially, Kriya said V greater than W is the Vedernikov. Is the concept that Vedernikov talked about in relation to the instability of the roll waves. That confirms that Vedernikov and Kriya criteria are the same. How about that? There's misspelling in there. I have to fix it. Let me write it down. It says craze. It's not craze. It's Kriya. Okay, we keep finding errors because we did this a couple of years ago. I had it redone by a student. And, you know, there's errors in there. Okay, the significance of the B over F ratio. The B over F is Vedernikov over fruit is equal to x1 minus D. We already defined that. Noted that the product of Vedernikov and the relative celerity leads to V times C sub D over equal V over F equal V over U equal to C sub K, which is the relative celerity of kinematic waves. So you may wonder, what is Professor Ponce doing here playing with algebra? In fact, we are. We're playing with algebra. There's various ways to talk about this thing, and you can equal, and say different things and mean the same. That's exactly what we're doing in here. Then the relative celerity of kinematic waves, or BF ratio, is significant that it is the only variable appearing in the exponent of the discharge area. In other words, V over F is determinant on the rating. And the rating is the Manning rating. Fundamental concept in open channel hydraulics is the uniform flow rating. And the V over F come inside the rating. How important that could be. We also kind of developed that, came up with that finding in this paper. Okay, so it's all explained in there. You have to spend some time on it though. Effect of boundary friction and cross-section. So it's clear that in order to determine the stability or instability, we had to figure out not only on the type of friction, and there could be 3 types of friction, laminar, turbulent, and mixed, and cross-section. And cross-section could be rectangular, or rather hydraulically wide, meaning rectangular, or triangular, which is specific triangular, or inherently stable, which is the stability that Liggett had talked about, and I put the name inherently in there just to make it strong. So that's the effect of the boundary friction. The role of a Vedernikov number in modeling catchment dynamics. And I should say at this point that I am still not sure, and this remains to be done, how important is the Vedernikov, in other words, how important is equation 6 as opposed to equation 5. Equation 5 is Hayami's, equation 6 is Professor Ponce's. And we believe that it is important when the flows get high. If the flows get more than fruit number equal 1, fruit number equal 1.5, then it becomes really important, because then when the Vedernikov is equal to 1, the diffusivity disappears. It vanishes, as you can see from equation 6. From equation 5, no matter what Vedernikov you had in there, the diffusivity was always going to be there finite. But that's not the true equation. The true equation is equation 6. So then at that point, and when the rollways start appearing, then diffusivity is 0, and that we know for a fact. Otherwise, we couldn't have it. Okay? Keep going in here. Case of the inherently stable channel further illustrate the concept of dynamic diffusivity. When the Vedernikov is 0, regardless of the fruit number, then Vedernikov square is equal to 0, and therefore velocity of dynamic equal to velocity of kinematic. So in other words, instability is produced when the dynamic wave, which is supposed to transport energy, when the kinematic wave, which transport mass, is trying to overcome the dynamic wave. At that point, they're about the same, and therefore all hell breaks loose, and nature responds by saying, I'm going to put a roll wave in here. So we know why roll waves are created. What we do not know up to this point, that's what I think, is why are they periodic? Why do you never have one wave, you have several. The pulsating waves of the Bolivians, they call it the pulsating waves. They don't have to call it roll waves. They have a lot of this, by the way, a lot of roll waves out there. And therefore, let me stop in here for a second. Okay, so let's keep going in here. Table 2 has the BF ratios. And you got to follow this on your own, by the way. I'm not going to get in detail in here. But in here, we already defined what D is. We defined what gamma. Gamma came from Vedernikov. V was defined by Vedernikov. X also defined by Vedernikov. And V over F is our ratio. And we have 3 types of cross sections: hydraulically wide, triangular, and inherently stable. And 2 types of friction. Here we did not add the friction in between, the Horton friction, because I didn't think it was necessary. I could, and anybody could sit down and put the intermediate values in there. You know, there's an intermediate value in there. For one thing, the V over F, the V over F in here is 3/2 to, what am I trying to say in here? Well, the intermediate values are in the middle. Okay. Now, the summary then of this paper. Vedernikov number is reviewed in the light of a new perspective of its role in the modeling of catchment dynamics using diffusion waves and incorporating inertial effects. In other words, in here, if you're going to do catchment dynamics with the Muskingum-Ganj, which is, by the way HMS does it to an extent, okay, we can incorporate inertial effects, and we can do that with the Vedernikov number. Together with the dimensionless relative celerities of kinematic and dynamic waves, the Vedernikov number is shown to properly characterize unsteady free surface flows. Like I said now, and I repeat, there is not one number in free surface. It's fruit that characterizes the steady, critical, supercritical, subcritical, or the Vedernikov that characterizes the unsteady, stable, or unstable. The ratio of Vedernikov to fruit numbers is shown to properly characterize the discharge area, the discharge flow area rating, which is a rating curve, because it's the only parameter that appears in the exponent. The Vedernikov number is also shown to have a significant role in extending the concept of hydraulic diffusivity to the realm of dynamic waves. This new perspective makes possible the modeling of catchment dynamics using diffusion waves and including inertial effects under a wide range of boundary friction and cross-sectional specification. We cover everything because the friction is either laminar or turbulent or transitional. Transitional or mixed. What's the difference? Transitional is a steady concept. Mixed is unsteady. In other words, you can have a steady flow, like in a pipe, steady flow in a pipe, right? The pipe is already covered. And you can have, if the Reynolds number is 500, you have laminar flow. If the Reynolds number is 2,000, you have turbulent flow. If the Reynolds number is 1,000, it's still steady flow, but it is transitional. The eddies are disappear. The eddies are starting to appear, and so forth. You already know all that from your fluid mechanics studies many years ago, several years ago in undergrad. Fluid mechanics, right? But that's for steady. Undergrad, fluid mechanics is steady. Grad fluid mechanics is unsteady. Okay? So that was fine at that point. Let me get in here. Now, as far as as far as the cross section, we already have three types of cross section. I'm losing it here a little bit. So okay, that was the friction. For the cross section, we have these three, and very, very well defined. Actually, not very well defined. The hydraulically wide, everybody knows. The triangular, everybody knows. But up to this point, when we followed the work of Liggett, people hadn't really worked on the inherently stable channel. And perhaps it is because it's an academic subject. The subject is so academic that the inherently stable channel has never been built. And in my sense, I don't think it'll ever be built because it's not necessary. You can put together a partially inherently stable channel that will do the job because the fruit number has an upper limit, as I already told you last time. And the inherently stable works for a fruit number equal to infinity. And there's no such a thing as fruit number infinity. So anybody that works on an inherently stable channel, well, they're doing it for the heck of it, but it's not going to have any practical significance. So why did Professor Ponce do this? Because we're not looking at practice. We're looking at theory. We're looking at understanding. And with this, we understood how it works. Okay, let me also say that back in the year 1982, regarding this subject, back in the year 1982, there was a gentleman whose name I do not know. I read the paper, okay? And he was working out in Colorado, and he was fascinated by the linear reservoirs. And the linear reservoir is a reservoir that has an outflow curve that is linear. Okay, you can do that easily in the computer. You can say V equal, or storage equal to KO, where the exponent of the outflow is 1, and therefore the storage is S equal to KO. That's linear. And then you use it in the computer, it'll come out with a linear reservoir. And the linear reservoir is a very important concept in hydrology. It provides diffusion, a certain amount of diffusion. Is not nonlinear, but it works. It works, and that also has given force or credence to the cascade of linear reservoirs, which is a model that we will talk about next week, and is very much used around the world. So the concept of linear reservoir is in mathematics and computers is very well established. What was not established was a linear reservoir built in the field. That had not happened. That was not there. So this gentleman decided he was going to do a linear reservoir in the field, and he did it. He did it. He published a paper on this. Unfortunately, I have not been able to track the paper down. I would love to. In one of these days, I'm going to go to the library, spend a few hours out there, try to figure out where that paper could be. It's hard to reference it because we don't have a reference. All we know that is what was in Civil Engineering magazine, not in ASCE journal. And it was around the early 80s. That's what we know. But I would go out there and look at all 80s, all the papers, so many papers, Civil Engineering magazine, and find and publish it and scan it and put it on the web because it was important. It was important because it was the first and perhaps only time where a linear reservoir was put physically in the field. Why would anybody want to do that? You got to be a little crazy like this guy. I'm joking here. But he said, I wanted to do it, and he did it. Okay? But the story doesn't end there, because the concept of the linear reservoir per se, like I said, there is a computational feature, and then there's the Colorado gentleman's feature. That was physical. But there's also a linear reservoir in sanitary engineering, which predates, well, not predates, but it's also very old, like maybe 30, 40 years old. The sanitary engineers developed over years a reservoir or a weir that would behave linearly, meaning the amount of storage is linear with the outflow, by constraining the cross-section, the same way the Colorado man did it, okay? Constraining the cross-section. That's called the Sutro spillway, or the Sutro gauge. Sutro spelled S-U-T-R-O. And I invite you to Google that stuff later on to find out if you don't know. You may already know. I may be talking stuff that you already know. But this is used in low flows, very small flows in sanitary engineering. So what is the comparison between the Sutro spillway and the Colorado spillway? They're the same concept, only the Colorado spillway is a full-scale, large discharge, while the Sutro spillway is supposed to be small discharge, because the people in sanitary engineering are dealing with small, generally, presumably, dealing with small discharges. Okay, so that's as far as I'm going to go on this paper. I urge you to review this paper, look at the math, make sure you understand everything I have said, because this is going to be on the exam. Okay, so that is good for the first paper. The second paper, dynamic hydraulic diffusivity, re-examine. You're going to be really surprised at this. So are you ready? Let's go for it. The dynamic hydraulic diffusivity, re-examine. With that exactly the title. We're going to be re-examining here this concept that was put together by the Polish gentleman. Who are they? Let's take a look. Doug JCI, W.B. Strupsevsky, and J.J. Napierskowski. I happen to know that these two gentlemen are from Poland. Not that they have Polish names. They do have Polish names, but they are actually from Poland. And in 1982, they wrote a journal hydrology paper called Hydrodynamic Derivation of Storage Parameters of the Muskingum Model. If you are not deterred by a challenge, okay, you can go in here and review the paper. Because we had the paper, we produced the paper, okay? All this stuff in here, as you can see, that's what I asked Nucitelli to review. And that's what we're going to try to put on our paper, okay? So over here, we're here. Dynamic hydraulic diffusivity re-exam. Okay, let's go on this one. The concept of the hydraulic diffusivity and its extensions to the dynamic regime are examined here. Hayami originated the concept in connection with the propagation of flat waves. He was the first one that said flat waves of diffusion are governed by diffusion, and let's derive an equation of diffusion, but it should also have convection. Cool. Doug extended Hayami's hydraulic diffusivity to the realm of dynamic waves, specifically for the case of Chessy friction in hydraulically wide channels. He's a professor, he was using Chessy. Fine. Doug's formulation amounts to a dynamic hydraulic diffusivity. Subsequently, Doug et al., that's the Polish gentleman, expressed the dynamic hydraulic diffusivity in terms of the exponent beta of the discharge area rating. And lastly, Ponce in 1991, A and B, I did it in both papers that I published in 1991, expressed the dynamic hydraulic diffusivity in terms of the Polish gentleman, in terms of the Vedernikov number, further clarifying the mechanics of flat wave propagation. Why they didn't do it? And the answer is because they presumably didn't know about the Vedernikov number. They just came up with some expression, this is it. But in reading their papers, I realized that what they had in there was a Vedernikov number. And it matched everything I had said in regards to my S-curve. So I went ahead and did it. There can be no other explanation for it. So, in other words, if you end up with a derivation like the Polish gentleman did, and then you have on the side a definition for the Vedernikov number, and it turns out that the Polish number, the Polish people end product looks and feels like the Vedernikov number, it is the Vedernikov number. There is no way out of that one. Okay? So the concept of hydraulic diffusivity is due to Hayami, repeated for the 10th time. Combine the equations of continuity and momentum to derive a convection diffusion equation, a partial differential equation containing a term of convection, first order, and a term of diffusion, second order. The modeling of flood wave propagation in terms of the convection diffusion equation has been referred to as Hayami's diffusion analogy. Although we don't like the term, but we repeat it here because it's very popular. The coefficient of the second order term is the channel hydraulic diffusivity, or Hayami's hydraulic diffusivity. I use that term in my book, by the way. Since he neglected inertia, Hayami purposely neglected inertia. He felt that it was not necessary at the time. He was working this in 1951. They didn't have any computers in 1951, and he didn't think it was necessary. And to a large extent, he was correct, by the way. By the time you include inertia, you end up climbing up the S-curve, and you end up in the Ferret area, in the Danny Ferret area, which is largely immaterial. Okay? So since he neglected inertia in his formulation, his hydraulic diffusivity is properly a kinematic hydraulic diffusivity. So here we gave it the name kinematic. So we said Hayami was kinematic because he neglected inertia. Everybody in the literature who neglects inertia ends up being kinematic, according to the notation of Leichert and Whittam. Dug extended Hayami's hydraulic diffusivity to the realm of dynamic waves, specifically for the case of Chessy friction in hydraulically wide channels. Dug's formulation is a dynamic hydraulic diffusivity. Subsequently, Dug et al., the Polish gentleman, expressed the dynamic hydraulic diffusivity in terms of the exponent beta. And then we came in later and said, oh, look at this. This is the Vedernikov number. So we wrote those two papers in 1991 saying that what the Dug equation should be looking after expressing it in terms of the Vedernikov number. The hydraulic diffusivity in terms of the Vedernikov number, that further clarifying the mechanics of flood wave propagation. These propositions are not explained in detail. I'm not going to go in detail on the math on this. I don't think I can at this point. It's not necessary. Well, I'm not going to say it's not necessary. Let's say we did it 90%, 95%, and then we ran out of will or whatever. But we have put it, all the equations that the Polish did, they're all in there for you to examine. Okay? I'm not going to quiz you on it, by the way, on the equations and how they got the equations. They had a lot of unusual assumptions. We don't want to call them weird, okay? Unusual stuff that we don't normally do. Hayami's hydraulic diffusivity, we already know that. Dug's hydraulic diffusivity, we already know that. We repeat it extensively. Dug's dynamic hydraulic diffusivity of the Polish gentleman looks like this. And why is it that? Okay. The variable beta in equation 3 is the exponent of the rating. The Polish were using M, by the way, in here. But I don't like M because I think M has been overused. So we were using beta. For Chessy friction in hydraulically wide channels, beta is 3/2. That we know. So if you put in there 3/2 minus this is 1/2. Square is 4. So you end up with this. That's a match completely. And I know these equations, I've been around these equations for a long time, and I know that they match. Okay, Ponce's dynamic diffusivity is the same, only that the F squared over 4 is interpreted now as the Vedernikov number. And believe me, we didn't get here lightly. We spent years looking at these equations. 85 to 90, 91, 90, 5 years looking at these equations. How come that long? Well, that's how long it takes when you're doing something new. Okay. Vedernikov is when V is the Vedernikov number, which we already expressed. I already explained to you what the Vedernikov number look like. That beta minus 1 is the x times the, what is the term, the number in there? It's the same as what Vedernikov said. The beta minus 1 is coalescence of those two terms that were in the front of Vedernikov's equation. As the fruit number goes to zero, the Vedernikov number goes to zero, and the dynamic hydraulic diffusivity reduces to the kinematic hydraulic diffusivity. In other words, Hayame's equation was applicable when the fruit number was very low. If the fruit number was 0.05, it was very applicable. You can, because it's a square. The effect is a square effect. The square of 0.05 is 0.0025 in this very small amount. On the other hand, when the Vedernikov number is equal to 1 or close, it gets to be close to 1, the diffusivity goes to 0. And this condition is the threshold of neutral stability. Because the diffusivity went to 0, the roll waves were able to produce. And again, I repeat here, we have not answered the question as to why the waves are periodic. We believe, and we're not experts in mechanics, that we have to have somebody that is really good in mechanics to understand why they're periodic. This has to do with what is called, in mechanics, is called modes of amplification. I studied this 40, 50 years ago, but I won't be able to repeat it at this point. But there's an issue here that remains to be determined. Under normal conditions, the fruit number is greater than 0. Of course, if the fruit number is 0, then there's no flow. Therefore, the Vedernikov number is greater than 0. Thus, the dynamic hydraulic diffusivity is always smaller than the kinematic. It's like almost 1, and then it's almost 0 when you get to Vedernikov equal 1. It varies between 1 and 0. In practice, the use of VK as opposed to VD will always exaggerate the amount of wave diffusion. A little bit exaggerated. Turns out that in practice it's a very small amount. In the limit for V equal 1, no diffusion is possible, and kinematic and dynamic waves travel at the same speed. They're not subject to dissipation, thus leading to roll waves, such as those shown in figure 1. I already told you that I went on a field trip in the year 2007, I believe, and they were showing me a project, an irrigation project. And they would just, this happened to be, when I was there, just happened to be releasing water through the lateral, I guess, to show it to me. They didn't intend to, but they did show it to me. So I took a bunch of pictures, and they're shown all over the place in my work, because they're nice and clear. Not to say that this is the only time. You already know, those of you that took my class, Open Channels, that these waves were first photographically documented by an Englishman named Cornish. He wasn't even an engineer, he was a geographer, because he was writing in a journal of geography. The Geographical Journal, which is a very reputable British journal, by the way. They just don't write anything in the Geographical Journal. But this guy was able to, because he came up with something interesting, because he showed a picture of something that had never been photographed. It had never occurred. Why had it never occurred? That's interesting. Because around the turn of the century, 120 years ago, people were getting involved in hydropower. Because prior, in the 19th century, there was no hydropower. It was all fossil. But then eventually we developed the machines, we got society in general. Europe, the United States, developed the machines necessary to extract power out of water. And then we had to convey the channels, convey the water, raise the water, or keep it up so that you could move the turbines and so forth when it fell. You know the story. But the point is that they had to construct canals, channels, rigid boundary channels in order to conduct the water to run it through the power plant, the hydropower plant. So they did. The Swiss did that, this in the early 1900s. And the paper by Cornish is dated 1907. I quote it everywhere. It's a good paper. Not in here, unfortunately. But as Cornish is published, Cornish is quoted in my book all over the place. Okay, so we have a paper by Cornish. Dr. Dressler, who was teaching somewhere out there in the East Coast in the 50s, studied this subject and came up with a procedure. Maybe he took out some pictures. So he's also well considered or well known when in the 50s he did work on the roll waves in the US, particularly here in the US, right? Because as you can see, this stuff was done all over the world. It was done in France, it was done in Russia, it was done by us in the US and so forth. So Dressler was also a player in the development of the theory and the practice of roll waves. And then we have the rest of the people following Duke, Polish gentleman, and myself. Okay, why not add it? We did that. We basically clarified, explained, and simplified. The word is simplified. Clarified and simplified mean the same thing. The issue, no longer to be considered difficult subject. It is a difficult subject, but it can be simplified and portrayed simply like the way we did. There's three velocities, there's two numbers. The numbers are Ferret and Vedernikov. So you can no longer afford to mention the Ferret without mentioning the Vedernikov, because there's two of a pair, and the third one is the beta. And that's why I said in my class that the beta is the most important concept, because it consumes, I mean, it subsums, I'm sorry, it sums, not consume, but subsums both of the major concepts, Ferret and Vedernikov. That's great, right? Now, the dynamic hydraulic diffusivity. And here we go now. This is the work of the Polish gentleman. In deriving the hydrodynamic Muskingum parameters, expressed x in terms of hydraulic variables. This including inertia. So he was going to come up with inertia, in which m is equal to that, n is equal to that. There's gradients in there. No, not gradients. Derivatives. Definitions, simplifications. P is equal to that, and R. You can look at where R is. In which y sub o, a sub o, q sub o are defined as such. The ratio m over n is this. Now, this is all algebra. The ratio, the first is, I guess you could argue where to get these numbers. They don't say, they just say, well, we got these numbers, okay? And then the ratio m over n, the ratio r over p, do define the variable m. That's the m variable that we're going to use. And this m variable is very much related to the Seddon law, by the way. You can see it in there. It's a Seddon law. Seddon law has a q and has an a in there. And here you got q and a too. Only that he's got two derivatives on top of it. The slope, the derivative of the slope with respect to the area and the q. And the variable m is the same as the exponent of the rating. Right, that's what I said. They used m, we used beta. And they keep going on with the math in here, from the definition of the Ferret number. That's the definition of the Ferret number. Everybody recognizes that. Then we end up equations 18 and 19. We replace 20. We get 21. And by the way, the algebra of this is correct. That's what I tasked Nucitelli with doing. You make sure that all the algebra is correct. And that's exactly where it was. Then the conveyance, definition of conveyance by Chow in his chapter 6. We already talked about that briefly. Replacing equation 23 and 21. Replacing 24 in 20. Replacing L with beta and so forth. And replacing equation 5 in 27. We end up with this equation, the kinematic diffusivity. We end up with this equation right there. Q sub s, the velocity, and you can see that. And we get to 28, and then we get to, because this is x of Muskingum, they were kind of focused on the Muskingum for whatever reason, I don't know. Because you could do this independently of the Muskingum. The Muskingum has nothing to do with this problem, as a matter of fact. But they were talking about it as if it were important. Apparently, what happened was, and I'm guessing in here, is that they started with the Muskingum and they ended up with their formula, which is not uncommon because they're using the same, it's the same concept that they're working with. After all, the Muskingum is a diffusion wave, right? And they were talking about diffusion waves. So the only thing is that they had to add in here the dynamic part of it, which the Muskingum never had. So they did that, and they ended up with this formula. And that's how they got the formula that we have presented as the dynamic hydraulic diffusivity, which is 29. So we ended up being in here, we summarized it in a calculator of the dynamic hydraulic diffusivity. These are the equations, the Ferret number, the Vedernikov number, the kinematic hydraulic diffusivity. So let's go over here, metric, flow velocity, let's say 2 meters per second, hydraulics 3 meters per second, bottom slope, something standard, exponent, well, let's say chassis. Chassis This is the well-behaved exponent. This is the better exponent. So with kinematic hydraulic diffusivity, the fruit number is 0.369. The Vedernikov number is 0.184. The kinematic hydraulic diffusivity is 3,000 meters squared per second. And the dynamic hydraulic diffusivity is 2898. So you can see the closeness between the kinematic, which doesn't have the Vedernikov, and the dynamic, which has the Vedernikov. It goes without saying that if the fruit number had been less, the Vedernikov number would be less, and these numbers will be closer. Like, for instance, let's take a look. Let's take a look here. Instead of putting a 2, let's put a 1. Actually, to make a point in here. 1.5. Now, you got 750 and 748. That's closer. You see? You see how it works? Easy. Okay. So we're running ahead of our time here. So now we are going to the next paper, the new perspective on the convection-diffusion-dispersion equation. Okay. I believe I already talked about it just briefly, but let me repeat it. Ferret, our friend Ferret, came out in 1984 with the convection-diffusion-dispersion equation. And he was the first gentleman that did this. And I read his paper, I liked it. I actually went and visited Ferret over in Dartmouth, because the Kriya lab, which is one of the 3 labs that the Army Corps has, the Kriya lab resides on the campus at Dartmouth. I think it's on the campus or right next to the campus at Dartmouth College out there in New Hampshire. So it was in the winter and I froze to death, but I ended up getting over there and meeting with Ferret. And we talked about his paper and some of the work that I had done. Needless to say, a great guy. But then afterwards, after working and reading many times the work that he had done, I realized that he did not complete the work. Great researcher. Remember, I told you about this. The only way you can do work is when the people that preceded us don't complete the work. If they didn't complete all the work, then we're stuck. Then we can't do anything. Okay, so he did not complete the work, so I pursued or proceeded to complete the work. So that's where we came out with this paper in the year 1989, I believe, 89 or 90. We published a paper in AGU, dimensionless convection-diffusion-dispersion equation. In other words, the convection-diffusion-dispersion equation had already been developed by Ferret. But he tried to non-dimensionalize it, but he failed. We talked about this already. Okay, so we're going to go in here and do what Ferret did not do. The coefficients of the dimensionless partial differential equation of convection, diffusion, dispersion of flat waves are shown to be functions of the fruit and Vedernikov numbers only. Well, why is this important? Actually, in practice, it's not that important. In theory, it is, and we should seek the theory in order to understand it. You would recall that when we read Duke, he was not only doing the third, he was doing the fourth. He was doing the 4th order. He came up with the 4th order. He was really ahead of his time with his mathematics that he had, the linear theory. He was doing the 4th order. He didn't give any name to the 3rd or 4th orders. Ferret failed short of doing the 4th order, but he did the 3rd. I'm sure he would have gotten a 4th order if you play around with the equations. You guys realize, of course, that the 1st order is the important one. The 2nd order is not that important. It's about 10% of the 1st order. The 3rd order is 10% of the 2nd order. And the 4th order is 10% of the 3rd order. So by the time you get to be looking at the 4th order, you're looking at a minuscule thing, very, very small. So in practice, it's not necessary. It really is not necessary. Even the 3rd order has proven against what Duke said in his paper. Well, he didn't say it. He just presented it because he's a math guy. Duke was a professor, a math guy. Here it is, guys. You can contend with it. But I can tell you from practice, given all the pluses and minuses and the ifs and buts in hydrology, and even in hydraulics, in hydrology, because this is routing, and routing is in the midst between hydraulics and hydrology. If people ask me, what's routing? I say, I don't know. It depends. Are you doing hydrologic routing or hydraulic routing? And what's the difference? That in hydraulic routing, you're taking account of the stages, while in hydrologic routing, you're not. Explicit account for stages, not in hydrologic routing. So that is why HECRAS does hydraulic routing, and HMS does hydrologic routing. HMS doesn't mess with the stages. And RAS doesn't do the conversion that HMS does. RAS doesn't do masking and catch, at any rate. So there's quite difference between those two. And those of us that do both sit in the middle. They sit in the middle. I realized that when I became a hydrologist in the year 1980, I, of course, was working with floods. I worked with floods from the beginning. And then I realized that, what do I call myself? Am I a hydraulic engineer or a hydrologic engineer? It doesn't really matter because I'm dealing with floods, and floods are in the middle. They're both. Anybody who says opposite or the contrary doesn't know what they're talking. They're both. So I ended up being both. Later on, not later on, at around the same time, people were saying, whoa, you know, let's call ourselves water resources engineers because that's what we are. We deal with water resources. And then the environmental movement came up, and some people were saying that water was not a resource because it gave utilitarian accent to the use of water. And that's true. We use water for specific purposes. But nature uses water too. And we got to respect nature. We should respect nature. So then the issue came about lately, only the last 10 years, that we really shouldn't be calling ourselves water resource engineers either. Because if we look at the whole thing broadly, then we should be just engineers of water, the water engineers. So that's why now we have come up with the idea that we should call ourselves water engineers in the future, because we deal with all kinds of things beyond just mechanics. Beyond mechanics and beyond hydrology, environmental hydrology, this and that. There is 106 definitions of hydrology. And for those of you that have not heard me talk about this, back 25 years ago, a colleague from India and I identified 54 definitions. And then over the years, since that 25 years ago, we have already come up with 106 definitions of hydrology. At the end of this class, I'll show it to you, or you can ask me for the link and I will send it to you. 106 definitions of hydrology. Professor Ponce knows maybe 10 or 15. The others, I do not know. And I would have to call the specialist so that they can handle it. Nuclear hydrology, for instance, is not my bag. Nuclear hydrology, isotope hydrology. For every one of these 106 subjects, there's a book or there's a very big reference. So we did not invent stuff. Professor Ponce doesn't invent things. I go to Google. If Google has it, it's okay, kosher. Okay. When we developed the concept of eco-hydroclimatology in the year 2013, I went to Google because we had eco-hydrology already, 20 years. We had hydroclimatology, but nobody had actually gone eco-hydroclimatology. So I went over to Google and I asked eco-hydroclimatology. And Google said, there's one link. Huh? One link? From India. A professor from India was teaching a course called eco-hydroclimatology, the combination of ecology, hydrology, and climatology. And of course, they're all three of them are tied together so profoundly that they're hard to separate. Now we know that. Okay, so then several years later, maybe 5 years later, about a couple of years ago, maybe this was in 2013. A couple of years ago, I went over and checked eco-hydroclimatology in Google. I wanted to see how the name had grown. And there were about 800 references. And now you can Google probably 2,000. It grows. Google grows with time. That is a fact. Okay, so we have the coefficients of the dimensionless partial differential equation of convection-diffusion-dispersion of Ferret are shown to be functions of the Freud and Vedernikov numbers only. So this is my story. I claim that there's the Freud number and the Vedernikov number, and there are no other numbers that relate in open channels. Now, the Reynolds number, yes, but that is not velocity ratios. Let's put it that way, because there's only two velocities, two numbers. And the third one is dependent. That's the beta. When you talk about viscosities, which is not velocity, then you can come up with some other numbers. As a matter of fact, we have two numbers, the Reynolds number and this other number that I should not tell the story at this point. Maybe at the end. Okay, remind me of this. But there's this other number, and we talked about those four numbers in the chapter 1 of our book on open channel hydraulics. So those of you that have taken open channel hydraulics have heard me talk about it already. But I said there's the Fru, Vedernikov, Reynolds, and this other number. I didn't give it a name because it has no name at this point. Something has to happen for somebody to ascribe a name to that concept. At this point, it has no name. So let me just leave it at that. The convection diffusion model of flood waves is improved. With the appropriate dimensional technique, the coefficients of the resulting third-order partial differential equation can be shown to be a function only of the fluid and Vedernikov numbers. This underscores the importance of these two dimensionless numbers in describing the dynamics of flood wave propagation. So this concept here verifies what I said. Let me also say that when I saw when I saw the Ferret paper, I immediately realized that he had not completed the work. I also immediately realized, I almost had a hunch. I said, this is Freud and Vedernikov again. And sure enough, it was. Okay? Because like I said, there's no other number. It would be extremely hard to think that out of this derivation, mathematical, physical mathematical, there was going to be another number in this equation, which was never shown in any other equation. That's not true, or it's not likely to happen. So the convection diffusion equation originally to Hayami, Doug improved the Hayami model, but including inertia, etc., etc. We already talked about this extensively. Ponce expressed the diffusion in terms of the Vedernikov number. Ferret derived the most complete third-order linear equation to date. We still have to derive the fourth order, which we would have to ask Doug. I think Doug died 10 years ago. I checked him. 2009 is when Doug passed away. He was at least 20 years older than I am. 15 to 20. Okay. Includes convection, diffusion, and dispersion. The issue of dispersion is a fascinating and interesting concept. What is diffusion and what is dispersion? Somebody asked me the other day that. And I said, well, it depends who you're talking to. They said, what? Yes, it depends who you're talking to. If you're talking to fluid mechanics guys, diffusion is the second order action on momentum. And dispersion is the second order action on mass. There's mass, momentum. Okay, dispersion of mass, dispersion of pollutants, right? Everybody understands that. However, when Ferret came about in the year 1984, he was going to work the third order. And he really didn't know what to call. I'm trying to guess here. I didn't ever ask him this. He didn't know what to call it, so he called it dispersion. And he was borrowing from the work of the numerical people like Conch and others that have had a need to name the third order error, and they don't know what to call it. So they've been calling it, as I have too, dispersion. So we use the term, in numerical analysis, we use the word dispersion loosely, sometimes to mean mass of the second order, and sometimes to mean, sorry, I can't speak anymore, to mean third order, as Ferret had done. So if anybody talks to you about dispersion, you should ask, what do you mean? What are you talking about? If you ask Google what dispersion is, they'll send you all over the place, because all Google does is repeat what other people have said, right? And it could be wrong. We say Google is 2% wrong. We still use it because it's convenient, it's easy, it's fast. It beats going to the library and spending a week in the library. In 1992 actually, I spent 3 months in the library writing a paper. 3 months, because I had to check the papers, and the papers were odd and the interlibrary loan and this and that. Right now it's a lot faster, right? Because we have Google. Google is a great tool, but it's not perfect, like anything else. Okay, so we have in here the Ferret equation, which you already know. We reviewed this in Ferret's paper. The convective celerity is defined as follows. 7. Okay, the flyway speed. Everybody knows this equation. Actually, no. I have a paper that I'm going to post for you. I'm going to write it in here. Post 7. I have a video on this in a tale, where I think I must have talked about this already, where I gave a lecture in 1987 to the Army Corps, and one of the guys said, Professor Ponce, you talk about the 7 guy. First of all, how you spell it, and second, what does he do? What does he do? He didn't know about 7, and he was a hydraulic engineer. Why didn't he? Didn't he have chow in his shelf? Everybody has chow in his shelf. Yes, but 7 is mentioned in chapter 18 of chow. And hardly anybody gets out there. Or they don't, they overlook it or whatever. So this is a famous formula by 7. The diffusion coefficient for Chesley friction in hydraulically wide channels, according to Duke, correct. Duke was apparently the first one to come up with this. And then the Fruit number defined as follows by Chow. Chow was an interesting guy. He hardly put anything on his own, but he wrote an excellent book, well-written book, that hardly had any errors. Actually, it had no typos. The guy was very meticulous. He must have spent hours, days, months editing and reviewing the paper to make sure that it had no typos. I can guarantee to you that Chow has no typos. So when I taught Chow, I couldn't find any errors. So I said to everybody that could listen, this is a perfect book. It has no errors. I said that because my book has errors, has typos. Isn't it amazing? Because we released it after 3 or 4 readings, and that's no good. You have to release the stuff after 10, 20 readings. And that way you'll get rid of the typos. But he must have done what Chow must have done. He had to do it. Okay. Later on, after reading Chow carefully, because I had to write the book, I realized that he's not perfect. I knew he was not perfect, but I now realize after reading his book, you realize that there's some things in there that don't make sense, but you really got to get profoundly into the book in order to find that out. Okay, so suffice it to criticize Chow here. So hydraulic depth, gravitational acceleration. In most cases of practical interest, the hydraulic depth may be approximated with the flow depth. That's true. The dispersion coefficient, following by Ferret. This is a formula presented by Ferret, okay? Ponce has expressed the convective celerity as a function of the fluid Vedernikov numbers. That's a formula that we have derived today for you. In 1991, that's a paper we just read. Following Dug, Ponce expressed the diffusion coefficient in terms of the Vedernikov number, in effect generalizing it for all friction types. So if I express it in terms of Vedernikov, I don't need to tell you the friction or the cross section. The Vedernikov already takes care of it. The Vedernikov number is supposed to take care of that. The Vedernikov is equal to x times the other function times the fruit, right? And x takes account of the friction and the other gamma. And gamma takes account of the cross section. So the Vedernikov number has already implicit in it the friction and the cross section. So that's the Vedernikov number. And that's our formula here. Dug 1982, that is correct. That's a Polish gentleman. And Ponce 1991. Okay, and now we just resort to algebra here. We get the diffusivity over here. The diffusivity 7 is expressed as 9 by using our L-Savoy. Our definition for L-Savoy, remember the characteristic length. And then we do the same with the dispersivity. We follow through with the dispersivity. And we end up expressing the dispersivity in terms of the L-Savoy. And we finally went to non-dimensionalize the convection-diffusion-dispersion equation. We define it this way. X prime, which is dimensionless, equal to x over L-Savoy, not over x. Not over what Ferret did. I forget what Ferret did. I think he used depth or something like this. We can go back. We're not going to do it, but you can go back in Ferret's paper and find out how he did it. But he wasn't using L-Savoy for sure. He did not know about L-Savoy. Okay, so we have these equations in here, and we end up with coming up with equation 11, which is equation of Ferret, but expressed now in terms of prime variables. X prime and T prime are dimensionless according to these equations. Now we have the celerity, dimensionless celerity, 1 plus V over F, that is dimensionless number. Dimensionless diffusivity, 1/2 of 1 minus V squared, that's also a dimensionless number. And N prime is a dimensionless dispersivity, which is also a dimensionless number in terms of fluid and Vedernikov. So how beautiful could this get? It can't get any more beautiful than this. And the reason is because all hydraulics is supposed to result in dimensionless numbers. That's the beauty of hydraulics. If you can't do it dimensionless, then you do something wrong, something empirical. If it's empirical, it's not dimensionless. If it's full-blown, how can I say, based on differential equations, then it becomes dimensionless, as you can see in here. So this paper is designed to show you the beauty of hydraulics, how beautiful it is that we developed 3 coefficients, and the 3 coefficients are a function of only of the 2 very important Freud and Vedernikov numbers. We have a calculation for the online dispersivity over here. And again, we're going to do a calculation in here, mean velocity, say 2 meters per second, flow depth 3 meters per second, channel slope 0.001. There's a standard slope, rating exponent 1.5. We do a calculation. Now look at these numbers in here. Through 36, that's exactly the same example that we had earlier. Celerity 3 meters, right? Because this is 2 meters, and celerity is 3 meters because it's got to be 1.5 the velocity. Diffusivity 393, and the dispersivity is very high. So you may wonder what the heck's going on in here, how on this number. Well, the dispersivity is very high, but it is affected or applies to a very low number. So by the time you get it, it's not that high. The coefficient is high according to definition, but in reality, it's not the same. And you can see when you talk about dimensionless numbers, it lowers down, it decreases down. So that's our answer or our explanation of the non-dimensionalization of the Ferret equation. The coefficients of the dimensionless partial differential equation of convection, diffusion, dispersion of flood waves are shown to be functions only of the Freud and Vedernikov numbers. The Freud number is the ratio of mean velocity to relative dynamic wave celerity by definition. The Vedernikov number is the ratio of relative kinematic wave celerity to relative dynamic wave celerity. The third order convection diffusion dispersion equation may be used in the analysis of flood propagation problems where both diffusion and dispersions are significant. Now, mind you, that's a very small amount of cases, but we're not talking practical here. We're talking understanding, theory. So that's the end of this paper. The Kriya paper is over here. I'm going to show it to you. Within the vast majority of gravity waves, I don't know what they call it, gravity waves. I mean, see, this guy has a problem with notation. He was coming from France and he was calling things the way we don't call it, okay? But I like this paper. He's a cool paper, but very complex to read. Oh. Let me see. Next page. No, I go to the next page in here. And next page in here. I want to get to some place that where I want to show you something in here. I hope I can get there. Yeah, he's talking about the QDW that's using omega. He's using omega for area. So he's talking about the Seddon waves. The Seddon waves. Okay, see, there's a mistake in here. The right hand is the inequality, is Lagrangian celerity. Lagrange celerity, we know the Lagrange celerity. For the elementary wave, yes, correct, it's a small wave. Under the exclusive action of gravity and inertia, that's wrong. It should be inertia and pressure gradient. There's no gravity involved in the Lagrange celerity. That's why there was a misnomer of calling it the gravity waves, which I followed, I had to follow. Remember I told you I couldn't rock the boat. I knew enough. I was smart enough to not rock the boat. You can't rock the boat if you don't own it. And I didn't own it at the time. So I call it gravity too. So I made the same mistake. It could be said that the same mistake I made, he made, but I don't think so. I don't think. I think he just was confused as to what exactly is the Lagrange celerity. So with that, having shown you that everybody, even the top people that are publishing in the best journals, actually do make mistakes. Mistakes happen. Okay, so at this point, I'm going to finish in here, and I'm just going to kind of show you a little bit, 5 minutes. We got 9 minutes, or 6 minutes, I'm sorry. So let's just look at this and see how we do this. Repetition. By the way, in my career, I have had a chance, luckily, how do I get rid of this? There we go. To ride several flood waves. I have ridden several flood waves, maybe 3 or 4 in my career. What do you mean ride a flood wave? Well, you have to be in the field at the time the flood wave comes. You got to identify the flood wave by it goes up and then it comes down later. And then you're in a boat, you're riding the flood wave, right? So this particular flood wave occurred in 1995 when I was finishing up the report on the Pantanal that you guys read. And I got caught in the middle of the river and a flood came in. That's a flood on the Cuiabá. This is the Cuiabá River in Brazil. And they have several others, which I have, by the way, posted in here because we're talking flood wave. We should show the pictures where we rode the flood wave. If you wonder what the music is, you can go back to the end. Is Offenbach, Barcarolle. The name of the music is called Barcarolle, which means, I guess in French it means boat. It's a boat on the water. Okay. So the coefficients, you can read this stuff. We already in the paper. Let me just start on the paper in here. I've pulled it, the quality of this picture is not that good. I pulled it out of the web. This is the town of Tlacotalpan in Veracruz, Mexico. This town sits right next to the Papaloapan River, which is the second or third largest river in Mexico. And it has a way of flooding every once in a while, like every 10 or 15 years. And this flood happened, I believe, 10 years ago, and it was a very bad one, major one. And you can see, you can look up Tlacotalpan flood 2010, 2011, and you'll get the videos. And I took this out of a video. I just did a screenshot out of a video so to show you the flood.
The convection-diffusion model of flood waves is improved with the addition of the third-order dispersion term, in effect constituting a convection-diffusion-dispersion model. With the appropriate dimensional technique, the coefficients of the resulting third-order partial differential equation can be shown to be a function only of the Ferret and Vedernikov numbers. This underscores the importance of these two-dimensional.
This is a flood wave that I wrote. This is the Piraí in eastern Bolivia. We were there to do an inspection back in the year 1990. That's 31 years ago. And we got caught in the rain, and all of a sudden we had a flood. Big flood.
Numbers in describing the dynamics of flood wave propagation.
This is an interesting picture. I was in Mexico, southern Mexico, many years ago, visiting. We were actually visiting a person. We wanted to visit a person over there that I happened to know when I was a child. And we ran into a flood. Professor Ponce runs into floods readily. We ran into the flood of the Suchiate River, which is the border. In other words, we were standing in Mexico, we were looking at Guatemala. Across the river is Guatemala. And this house had just was in the way of falling into the river. So it was an interesting picture to take.
The convection-diffusion model of flood waves is originally due to Hayami in 1951. Doob in 1973 improved the Hayami model by including inertia in the formulation of the diffusion coefficient, resulting in a convection-diffusion model with inertia. Doob et al. In 1982.
This is a picture of a flood overtopping a bridge. Fascinating. This is in Peru. This was the flood of 2017. The flood of 2017, the year 2017 was an El Nino year, and it had an effect throughout the Pacific. Here, it almost broke the Oroville, right. Oroville Dam was almost, the two spillways at Oroville were almost destroyed by the flood. And this is in Peru, where they had many situations where the towns were all overwhelmed with water. This particular town was overwhelmed with water. The water is going over the bridge, as you can see.
Generalize the convection diffusion model with inertia for any friction type and cross-sectional shape. Ponce, in 1991, expressed the diffusion coefficient in terms of the Vedernikov number. Ferret et al. In 1984 derived the most complete third-order linear.
I'm going to stop it in a minute, because we're running out of time.
To date,
you can finish on your own.
Convection, diffusion, and dispersion processes, to wit, in which Q equal discharge, C convective celerity, nu diffusion coefficient, and eta dispersion coefficient. The convective celerity or flood wave speed is defined as follows, in which A equal flow area. The diffusion coefficient or hydraulic diffusivity or Chessy friction in hydraulically wide channels is in which Q sub O equal unit width discharge, S sub O equal bottom slope, and F equal Froude number, defined as follows, in which U sub O equal mean velocity, T sub O equal hydraulic depth, and G gravitational
Okay, so
acceleration.
you can pursue the finishing of this movie or this video on your own. It is repetition of what we have already said in vector form, by the way. Okay, thank you very much.
Or hydraulic dispersivity is.
Where's my arrow? The arrow is gone. I can't figure this Zoom thing out. Okay, see you later, guys.